Hello everyone. Welcome back to our pre-recorded lectures for Chemistry 1010. This is the pre-recorded lecture that belongs with Tuesday, March 24th. In this particular pre-recorded lecture, we're going to be starting the content of Chapter 5, Gases, which would also show up as the notes as Module 8. And what we'll really find is that we're essentially in this chapter focusing only on some of the bits and pieces, unlike chapters 1 to 4 where we covered the entire content of those chapters. In this particular chapter, we are going to be focusing only on some bits and pieces. Effectively, we're going to focus on the properties associated with the gas, the variables that we use to describe the properties of gases, some simple connections between those properties and what we call the simple gas laws, which would ultimately then be combined together to create a single description of the behavior of a gas, which is called the ideal gas law. But we're not going to focus on the ideal gas law in this course. And that is because most of you will be transitioning from Chemistry 1010 into Chemistry 1050, where Chapter 5 is the first chapter that you will see in that course at Memorial University. In other words, you're going to see some of this stuff again when you take 1050, if that's the path through chemistry that you're taking as you explore your degree options. So yeah, once we have that idea of the ideal gas or the gas laws and how they work together, we're really going to try and connect that to the most important aspect for this course, which is yet another means of showing us how we can look at amounts of stuff in chemical reactions. If those chemicals are found in the gas phase, we can actually make some comparisons. That means we can directly figure out kind of amount of stuff by looking at another property, like let's say the volume of a gas. We're not going to go into the nuts and bolts of why a gas behaves like it does. That is something called kinetic molecular theory of gases. That is going to be, again, something that you would see in a course like Chemistry 1050. You will also notice I have not started this particular lecture with any bookkeeping. As I would have mentioned in yesterday's good 20 minutes of bookkeeping, I'm going to be reserving most of the lecture time for actually talking about the content of the course. So if you want the latest information in terms of COVID-19 and how Memorial University is handling that and what decisions have been made, of course you want to go to the university webpage for that purpose, mun.ca/COVID-19. For information as it relates to this course, those bits of information are essentially being given as announcements in the Brightspace shell for this course. We talked through a lot of those yesterday, the most recent ones, in terms of the Chemistry Virtual Help Center and the idea of a second chance midterm for those who missed it, and to give everyone at least one more attempt at improving upon their mark for the midterm exam. All that because we are now not going to have a final exam in this course. I'd rather let you have the opportunity to focus on your other courses, whereas a lot of the evaluation and understanding that I would expect you to be able to handle from this course is going to be doable through the daily assignments and Brightspace quizzes and things like that. So if you want a little more detail about how that's handled, you can check out the March 23rd lecture and again the announcements in the Brightspace shell. But I want to focus today on talking about gases and moving forward from there content-wise. So let's actually start talking about gases by saying, well, what is a gas? We have some ideas, most of us. We all know that the air around us is really a mixture of gases, predominantly molecular nitrogen, some molecular oxygen. We've got some carbon dioxide in there, we've got some argon, and we've got a few other gases floating around, but nitrogen and oxygen are the vast majority of that. Now, those gases have properties, and those properties we can usually think of in terms of our experience with either balloons or, let's say, a gas cylinder like a helium cylinder that you might actually go and see at the grocery store or the party store, which they use to fill those same balloons, let's say, for a birthday party. And so one of the first properties that we see for gases and have everyday experience, and again, this could be blowing up a bike tire or a car tire, tire on a wheelbarrow, anything like that, is we know that gases will tend to expand and fill and take the shape of the container they are in. They're going to fill the container in that the gases will effectively be everywhere in there, and by the gases I actually mean the atoms or molecules that the gas is actually made up of, they're actually occupying the entire container. So when we blow up a balloon, effectively the size and shape of the balloon, well, the shape is really more determined by, let's say, the rubber or the mylar, but effectively we always see that the balloon is trying to be the biggest version of that shape that it can be under the current conditions of what's happening in the world around it. Gases also take the shape of the container they are in. In other words, effectively, we're saying gases are fluid. So if we think about liquids, which are also fluids, we know that they take the shape of the container they're in. If I could somehow make my coffee cup invisible here, you would see the liquid coffee has the cylindrical shape of the coffee cup interior itself. It would have to, because that's what's happening. And gases will do the same thing, whereas really the only difference between a gas and a liquid is while this liquid in my coffee cup does not expand to fill the entire coffee cup, it actually sits in the bottom. If I had some sort of cover on this and I fill this in gas, then there is going to be gas spread out evenly throughout my coffee cup. That's really the biggest difference between the idea of filling and taking the shape as opposed to not being able to. But the idea of taking the shape is really connected to the idea of fluidity, and both liquids and gases have that. We'll also see, according to the slide, that gases can diffuse and mix in all proportions with each other. So if I went to some other planet around some star far, far away, maybe in a galaxy far, far away, long, long ago, effectively what we're going to find is there's going to be an atmosphere for that planet, and maybe it's a nitrogen and oxygen and carbon dioxide and argon atmosphere exactly like we have on here on Earth, but we might find that the proportions might be a bit different. It could be 60% nitrogen instead of 78%. There could be, let's say, 20% oxygen instead of 16%. But really, at the end of the day, we can essentially mix together gases in any kind of relative combination of amounts that we want. And that's all because the gases can interpenetrate. It's not like we're going to have one gas sitting here, another gas sitting here on top. Rather, the gas molecules are going to combine and mix into effectively what we would call a solution of gases. Solutions are going to be something that you're probably going to see more in a course like Chemistry 1051. Now, it turns out that if I want to describe a gas and its properties, it turns out there are 4 state variables. And by state variables, effectively 4 pieces of information that we can know about that gas. And it turns out once we know any 3 of those 4 pieces of information, we would always be able to figure out the 4th piece of information as long as we have the mathematical connection between the pieces of information in what we would call an equation of state. And while, again, we're going to look at the simple gas laws, looking how any 2 of these variables kind of connect to each other, we could then combine those simple gas laws into an overall equation we call the ideal gas law. That would be the equation of state that would help us understand the properties of this thing that we call an ideal gas. Ideal is obviously giving you a hint that there's something about it that is very what's the word other than ideal that I can connect to it? There's something kind of perfect or very understandable in the behavior. We all have our ideals of, the person we would like to meet, or the ideal situation we would have for our career. That's essentially just our beautiful rose-colored glasses view of the world. And we all know that reality sometimes kicks in, and you find a person that you want to be with, you find that career, and every once in a while things just aren't going to be perfect. And that's okay. But sometimes the best way to understand how the world works around you is to look at the simplest, most perfect way, and then we can try and understand how the differences come about because of some of the ideas or assumptions that we based our perfection on may need to be changed a little bit in that particular case. That's, again, if we go into the full ideal gas law, again giving you an introduction of what this chapter may take you to once you see it in a course, again, like Chemistry 1050. So let's talk about those variables, those properties, those things that we use to describe gases in terms of our understanding of their behavior. So when it comes to that, The state variables of the gas, again, we've got 4 of those. The first one of those state variables is the amount of gas we have. Now, again, a gas is made out of atoms or molecules, which means we're talking about gases could be chemicals, the chemicals that we involve in reactions. And we just spent a whole module, a whole chapter talking about balancing equations because chemistry ultimately needs to be done by number of pieces and not how heavy the pieces are. And so if we're going to talk about the state variables of the gas, and the first one we're going to talk about is the amount of gas, it shouldn't surprise us that the way we are going to essentially evaluate the amount of gas is going to be in terms of moles, literally counting individual gas molecules, but again, grouping them together in the chemist's dozen, which is the mole. And of course, we have to remember from our earlier modules that the amount in moles is related to the actual individual number of gas molecules through Avogadro's number, 6.022 times 10 to the 23 per mole. And again, that could be per mole of anything. Could be per mole of gas molecules, could be mole per mole of sheets of paper, for example. That's a whole lot of paper, but again, it's no different than a dozen eggs versus a dozen gummy bears. It's still going to be 12 in that particular case. Now, if we know the number of moles of a given gas, and of course we've seen that chemicals and chemical compounds have a connection between moles and something more easily measured like the mass through the molar mass, then of course what we're going to find is if we recall that the molar mass is going to connect the mass to the number of moles, then what we would find is if I had equal masses of different gases, that's actually going to represent different number of moles of each. So if I have 10 grams of nitrogen gas and 10 grams of oxygen gas at the exact same conditions, then it turns out I'm not going to have the same number of nitrogen and oxygen gas molecules because oxygen molecules are a bit heavier. Effectively about 32 grams per mole for molecular oxygen versus 28 grams per mole for molecular nitrogen. So if I wanted to have equal number of moles of nitrogen and oxygen, I'm going to have different masses for those gas samples. For example, 28 grams of nitrogen is 1 mole, 32 grams of oxygen is 1 mole. Now I have the same amount. And again, that's going to be important because if I want to do chemistry involving, let's say, nitrogen and oxygen reacting together to give us, let's say, something like nitrogen dioxide, there's going to be a balanced equation associated with that. And again, the connection is going to have to be by the numbers of atoms, not the masses that we have. I'm going to take just a wee little break to enjoy that coffee cup that I was talking about. There we go. So that's our first state variable of a gas, the amount. The second state variable is the volume of the container holding the gas. Again, we're used to balloons, tires, all sorts of things that contain gas in the world around us, and we know that balloons and tires come in different volumes. There's the tires associated with tractors or tractor trailers or big mining trucks versus the little tire on the end of a wheelbarrow. All sorts of different volumes. And of course, you can buy balloons of varying sizes as well. So, we've really seen volume already. It's one of the kind of earliest things we talked about when we talked about derived units in the early modules. Essentially, we've seen that volume, while we tend to, in our everyday life, at least in the metric system, tend to express volumes of stuff around us in liters. You go and buy a 2-liter carton of milk, for example. Again, this is really a derived unit because volume is effectively the cube of distance. As we see in this case, if I have a cube 10 centimeters by 10 centimeters by 10 centimeters, then really what I have is a liter in that particular case. And that means our ideas of the earlier modules about conversion factors, where 1 liter equals 1 cubic decimeter or 1 milliliter is 1 cubic centimeter, that means because we can express volume in so many different ways. We have to be prepared to use conversion factors to get answers in a different unit than we may be given data for, or just to get used to the idea that, look, the world has measured things in many, many different ways. We're going to see that again for some of our other variables. Variable like amount in moles, we don't have really any other options because moles is the most obvious case for measuring things in chemistry, whereas volumes, cubic meters versus liters, is a difference that we could have in terms of how we're seeing information. So make sure that if you're still not all that comfortable with your conversion factors, that you keep working on those, because that's going to be a big part of some of the problem solving in this chapter. Our next state variable is the temperature. Effectively, what we're going to find out is that temperature in many ways is a reflection of the average energy available to a molecule in a chemical system. As the temperature goes up, that molecule has more energy available to it, and really since energy, or at least what we think of as kinetic energy, the energy of motion, has a very simple equation. The kinetic energy is 1/2 the mass times the velocity squared. Effectively, what we find is that if we increase the temperature of a chemical system, of course the molecules cannot get any heavier. They are not changing their chemical identity. They're not changing the elements they're made of. That means if I heat up a gas, increasing its temperature, really what I'm doing is making the molecules of that gas move faster. And of course, faster moving things, if you get hit by something moving faster, you're going to feel a bigger transfer of energy. Turns out that connects to the idea of our fourth state variable, which we'll see in a moment. Again, we're not going to get too deep into the ideas of kinetic molecular theory. That is a concept for chemistry 1050. But I'm trying to give you an idea of how this will connect, because many of you will eventually go on and see gases in more detail. Now, of course, the interesting thing, as we would have seen again when we talked about units and measurement very early on in this course, when we measure temperatures in chemistry, we want to generally do those in Kelvin. It turns out there's a very, very good reason for that, especially when it comes to the calculation of gases, as we will see with one of our simple gas laws. But it turns out that effectively what we call the Kelvin scale is actually based on the behavior of gases. And if we imagine what that gas behavior would look like as we keep cooling things down more and more and more, taking energy away from those molecules and slowing them down. You've got to imagine at some point we're going to be able to take all the energy away from those molecules that we absolutely can, and those molecules should really stop moving. At that point, that would describe some sort of very interesting temperature about the world around us, and it turns out that that is a very important thing. So again, we've seen that if we want to measure a temperature for a particular thing in Kelvin units, we need to take the temperature in degrees Celsius and effectively add 273.15. What that means is the size of a degree Celsius and the size of a degree Kelvin are the same. The only difference between the two scales is where we say 0 is. For the Celsius scale, 0 is the freezing point of water. The size of a degree Celsius is determined effectively by the fact that we set the boiling point of water as 100 degrees Celsius, and so the size of a degree Celsius is 1/100th of the difference in temperature between the boiling and freezing point of water. What we see is in the Kelvin scale that we have the exact same difference, 273 Kelvin for the freezing point of water, 373 Kelvin for the boiling point of water. That's again a difference of 100 degrees. And since we have the same 100-degree difference, and we want to break things into equal sized chunks in our temperature scale, that must mean a degree Celsius and a degree Kelvin have the same size. So what's the difference? Well, we said, look, 0 is here at 0 degrees Celsius, the freezing point of water in the Celsius scale. In the absolute or Kelvin scale, what we're going to find is 0 is that particular temperature where we have stolen every bit of energy we can from the gas molecules, effectively to the point where they can no longer move. And it turns out that at that particular temperature, every substance in the universe would have given up all the energy that it's allowed to, and so there is no more energy that can be taken away. It's not like I can cool down this gas to one particular temperature and have taken all the energy away, and take this other gas, cool it down to a different temperature to get all the energy taken away. All the energy getting taken away is going to be the same no matter what substance we talk about. And that's why the Kelvin scale, 0 Kelvin, is referred to absolute zero. There is no temperature colder than that is possible, since again, temperature is really a measure of the energy the molecules have. When you have no energy, you have no temperature. And again, we have to be careful. You do have some energy. There's just no more energy that can be taken away. So your lowest possible energy is really what that means. Our fourth state variable for a gas is the pressure. Now, most of us have a sense of what pressure is. Obviously, if you are going into writing an exam or something, you feel the pressure of the situation. Often it's also called the weight. In that particular case, you're feeling the push on you. Another case where people really understand pressure is if you like swimming in a swimming pool. As you dive down, you get squeezed more and more. The deeper you go, you can feel the weight of the water above you. And in fact, that's going to be a big part of our understanding of pressure. Because really what happens is pressure comes about from the fact that those molecules of gas that we're talking about, they've got a lot of empty space in between them, which means those molecules, if they're at some temperature above absolute zero, are moving. Higher temperatures, they're moving faster, is in fact what we would find. And if you're moving around in a container, eventually you are going to hit the wall. And when you hit the wall, just like my hand now hurts because I hit it against my other hand, there was a transfer in energy when one hand hit the other. The same thing happens when a gas molecule hits the wall, like it is right here. It's going to exert a force on the wall. It is going to push. Of course, by Newton's laws of mechanics, the wall is going to push back equally. But in the meantime, it's really that push that is going to create this thing that we call pressure. Now, pressure is not the force itself. There's another factor we have to consider, and that is the idea that the force can be spread out over an area. And the example I like to use for this is if I came into where you're watching this lecture and I stood on your foot, yeah, that's going to hurt. You're going to feel the weight. You're going to feel the pressure of me stepping on your foot. The question is, what's the difference if I step on your foot wearing, let's say, a nice big clown shoe that we often associate, the big floppy shoes of a clown, or if I wear a little stiletto heel? So if I put all my weight onto your foot while I'm wearing a clown shoe, all that weight is spread out over a much larger area, that big floppy sole of the clown shoe. If I take that same weight, because I have not changed in the moment it took me to take one shoe off and to put another shoe on, and then I step with all my weight on your foot with a stiletto heel, which has a small area like this, you are going to feel that a whole lot more. It's the same force, the same pull down of my mass by gravity onto your foot, but it's now concentrated into a much smaller area than it was before when I wore my clown shoe, and that means that you are going to feel more pressure. So the molecules bang into the containers of the wall. They actually also bang into each other as well, but that's a secondary kind of thing for our understanding of pressure. And that means they're going to exert force on the wall of the container. That force has to be divided by the surface area, as we're going to find out on the next slide. So effectively, the SI unit of force is the Newton. That's a derived unit because force is mass times acceleration. So 1 Newton is a kilogram meter per second squared. So here we see the derived unit. Here we see the 3 different base units that comprise that derived unit. And once we understand the force exerted by a collision of a molecule, then we essentially have to think about the net force. All the gas molecules colliding over a given time period. That's going to give us a total amount of force. That total amount of force has to be spread out over all the surface areas of the walls of the container, whether it's a spherical balloon, whether it is a square box, cubic box, does not make a difference. What we need to know is the given surface area. Floppy clown shoe, big area. Stiletto heel, small area. Floppy clown shoe with a bigger area, same force, means lower pressure compared to that stiletto heel with the same force. So it turns out the actual unit for pressure in the international system of units is also a derived unit. That derived unit is the Pascal. You're going to notice that a lot of units are given names of scientists who did a lot of work in those areas. Pascal is no different. Again, just a note of interest. The name of the unit, even though it's based on the name of the person, the unit name itself, in other words, the actual Pascal, is not capitalized. The unit for many of these is capitalized. So we had our Newton, another named unit, capital N for the symbol, but when we actually look at the word Newton, it starts with a lowercase n, and so on. That's just kind of a standardized way of looking at units, and that's going to be true for many, many, many of the units that we see named after people. But yeah, that Pascal, again, is really the pressure. That's force divided by area. 1 Pascal, well, we saw force is a Newton, so if area, that's effectively a square footage, for example, like a carpet. But of course, we tend not to do stuff in feet. That is not the SI unit for measuring a distance. The SI unit is, of course, the meter. So if I want to measure an area, it's in square meters in that particular case. So 1 Pascal is 1 Newton per square meter. Obviously, we could then take the derived unit of Newton and break it into its pieces, kilogram meter per second squared. And so the Pascal, it turns out to be another derived unit, which is a kilogram per meter per second squared. Now, it turns out the Pascal is actually a very small unit of pressure. In fact, it's so small that most of the time we will tend to talk about pressures in the SI units with a metric prefix. That metric prefix is going to be kilo, because most pressures of the world around us, like the atmospheric pressure, happen to be in the order of kilopascals, thousands of pascals. And in fact, the pressure of the world around us, the atmosphere around us on any given day, is usually close to 100 to 101 kilopascals. In other words, we're talking about 10,000 pascals is kind of the normal pressure of everyday life in the air around us, at least on planet Earth. I know some of you have had to go home during this whole COVID-19 thing. I don't think any of you have gone to the moon or Mars. So luckily, at least there's one thing we all have in common. That's the pressure of the air around us. So, 4 state variables. Well, of course, many of you know by now that I tend to like to use analogies to get points across, to get a better understanding of what's happening, because sometimes you have to be able to attach a picture to things, this picture that isn't these little gas molecules that you've never seen whizzing about banging against walls. So really, our analogy for gas behavior is going to be a bouncy castle. And I love this analogy for 2 reasons. That's because the bouncy castle itself is effectively a big balloon filled with gas. The whole reason it's got structure and form is effectively the idea of gas molecules hitting the walls, creating the balloon-like kind of folds of our bouncy castle. And therefore, we are technically talking about gases inside the bouncy castle. What I'm going to use as the analogy for gas behavior is the kids inside the bouncy castle. Most of us have seen a bouncy castle. If you've never seen one, I think the picture is pretty clear. It's effectively this big balloon that you can go in and jump around and, do things like being a kid. Many of you have probably seen a bouncy castle, whether you took your kids or your niece or nephew or some other child family member down to Action. They've got a whole bunch of bouncy castles. Of course, they show up at the regatta if you're in St. John's, and things like that. And of course, you could rent one for a birthday party. So if you never had a bouncy castle at your own birthday parties, again, you might have family members who have. You've possibly seen a bouncy castle in person. So, of the 4 state variables of the gas, we can explain those 4 state variables and connect them to an easy to think about picture of kids in a bouncy castle by connecting those 4 state variables to the actual things that are happening. The pressure is really the kids hitting the walls of the bouncy castle. Here we see, yeah, I know it's blurry because it's a nice action shot. That's because everything is moving. Well, here we see a kid bouncing against the wall. We, in fact, have seen the wall has bent out a little bit. That's force being exerted on that particular surface area of that part of the bouncy castle right now. That is pressure happening right now. We see this kid here has just landed, as has this kid. They're exerting pressure on the floor of the bouncy castle through that particular situation. So the pressure is literally the banging into the walls that the kids are doing. They're transferring energy to the bouncy castle itself. V, the volume, of course, is how big the bouncy castle is. This bouncy castle looks like it can hold safely about 10 kids, maybe 12. There are other bouncy castles out there that are better suited to hold 5 or 6 kids, and maybe you could come up with a super bouncy castle that could hold 100 kids. And so effectively, all we're doing is changing how far apart the walls are and the floor and ceiling are from each other. It's just a, in this case, nearly box kind of shaped thing. And so, of course, the size of the bouncy castle can change. The temperature, in this case, is effectively how much energy the kids have. Again, we said temperature is really a reflection of the average kinetic energy of the molecules. As temperature goes up, the molecules are effectively moving faster. And so the analogy I like to use, again, because bouncy castles are often found at children's birthday parties or things like that, is, okay, well, if the kids show up at the birthday party, they jump in the bouncy castle. It's like, hey, yeah, we're having some fun. And then you get them out and you feed them some chips and you feed them some soda and you feed them some cake and ice cream, and now they are hopped up on sugar. And most of us know that when you have a kid and you give them a whole bunch of sugar, they become a whole lot more active. They become a whole lot more energetic. So increasing the temperature of a gas is no different than giving kids sugar. They're going to go back into the bouncy castle that they may have enjoyed before all the snacks and whatever, and they are going to be, if I'm going to use a very nice word for it, maniacs when they're in there. They're going to start bouncing against the walls literally harder than they were before because they've got more energy to do that. And of course, our last state variable, M, the amount, well, of course, that's amount of gas. Well, amount of kids doesn't really change our understanding. Right now, again, we have about 10 kids in the picture in the bouncy castle. It looks like we've got 3 more about to get into the bouncy castle. And so, of course, we would have increased the number of kids. That's like blowing more air into a balloon. There's now more gas molecules, more stuff able to hit against the walls at any given time. So we've got about 15 minutes left in this particular lecture, so that's going to be plenty of time for us to introduce the simple gas laws, or at least the first 1 or 2 of them, do a little bit of problem solving, and then when we come back for Wednesday's pre-recorded lecture, of course March 25th's pre-recorded lecture, we will continue on from there. So this is supposed to be a slide about liquid pressure. That does not seem to be working. So let's try and do the fix. For whatever reason, my PowerPoint did not like that for a moment. So yeah, seems like we've fixed that. So let's talk about liquid pressure for a moment. Because liquid pressure, again, is something that we actually have some experience with. Most of us can swim. Most of us have been in a swimming pool or a lake or a pond or the ocean. We have dived down under the surface of the water, and we know as we go deeper and deeper and deeper under the water, we start getting pressed more and more and more on all sides by effectively the weight of the water pushing down on us. So liquid pressure is a concept we have. Even if you have never been in a swimming pool, you do not swim, if you have washed your dishes, if you have taken a bath, you will of course feel the weight of the water on your legs or your hands in the dishwater, because you can feel the pressure. There is weight to that water that is pressing on all sides. And really what that is liquid water molecules banging against your hands or against your body and essentially applying force. That is the pressure you feel in that particular case. So why are we talking about liquid pressure when this whole chapter is supposed to be about gases? Well, it turns out that liquid pressure is very easy to measure because pressure is, again, force divided by area. And force is mass times acceleration. And the acceleration that we could be talking about in this case is the acceleration due to the force of gravity. So all of a sudden, when we talk about mass times acceleration, well, there's another equivalent to that when we think about something being pulled down with a certain mass under the acceleration due to gravity. We call that weight. And so if I want to measure liquid pressure, I really just need to measure the weight of the liquid pushing down compared to some sort of evened or standardized kind of situation. So effectively, the force exerted by a column of liquid, measuring that is easy. I just pull out a balance and I could literally weigh that. Turns out I don't even have to do that, because at the end of the day, I could even measure that pressure just in terms of the amount of liquid that I have pushing down, because of course the force of the acceleration due to gravity is relatively unchanging no matter where you are on the Earth. There are some kind of localized differences. If you're on top of Mount Everest, you experience a little less gravity than you do at sea level in St. John's, but we're going to assume that we're really talking about the same gravitational attraction, acceleration, no matter where you are on the Earth. So in fact, it was this idea of liquid pressure which led to our earliest ways of measuring the pressures of gases. Effectively, what we're talking about is measuring a gas pressure by using a liquid pressure proxy. And it turns out the piece of equipment that historically has been used to do that is the barometer. And that barometer can be used to measure what we call the barometric pressure, which is really the pressure of the gas around us. That is the atmosphere of the Earth. And so what we see here is this. On the right-hand side of this particular picture, we see a very interesting setup. We essentially have just a big bowl full of mercury. This is one of the historical parts of barometers that you're not going to see much anymore. We tend to try and not use big amounts of mercury if we don't have to. Mercury vapor can essentially settle in your brain and cause damage. So yeah, we don't like to use mercury all that often. For those of you who are familiar with the book Alice in Wonderland, of course, one of the characters in that book is the Mad Hatter. And the Mad Hatter was named such because hats at that time in Victorian kind of day England were often made out of felt, and part of the process of making felt was giving it color, and a lot of the colors of felts were given to them by using mercury salts, which means that hatters were using mercury a fair bit. And of course, that started building up in their systems, including their brains, starting to cause actual literal brain damage, changing their behaviors. So a lot of hatters were considered to be a little strange in that particular case. And mad might have been a better word used by, let's be honest, Victorian society, who were not necessarily the most elegant in their treatment of mental affliction, unfortunately. Of course, we're doing much better, but we still have a long way to go in that regard. Anyway, we've got this bowl of liquid mercury, and effectively what we would have done is taken a test tube or something like that with one closed end and one open end and poured in a whole bunch of mercury into that tube until it was full. And then very, very, very carefully, we would have to find a way to invert that tube full of mercury into the pool of liquid mercury in the bowl, like we see here, so that none of the mercury came out of the tube. Now, what you're going to find, though, is once you've inverted it in the bowl, some of that mercury will have run out of the tube to spend time in the bowl. When that mercury leaves this part of the tube, there's nothing there to replace it. Because we had it full, the tube, of mercury, there was no gas in that tube. By inverting it over there, what we've done is effectively create a vacuum, a volume of space that has nothing in it. Technically not true. There's mercury vapor and a whole bunch of other things, but for our purposes, we're saying there's nothing there. It's no different than deep space in that particular case. So what you're going to find, though, is not all of the mercury would run out of the tube. At some point, we're going to see mercury run out of the tube, and then it's going to stop. It's going to stop, and we're going to find out it's going to stop when the level of mercury in the tube is about 760 millimeters, 70 centimeters higher in the vacuum side of the tube than it is where it meets the pool of mercury. Why is that happening? Because we have to realize there's actually two things happening here. As the mercury was running out of the tube, effectively what we were doing is taking a column of mercury and making it shorter. In other words, we have less mercury pressing down, being pulled downwards by the force of gravity. We have less weight of mercury. Now, if there was no opposing force on the other side, that would keep running out until the two levels would be even. Think about putting a straw into a drink. If you actually look down the straw, you will see the level of liquid inside the straw is the same as the level outside the straw. Why is that? Because you've got air pressing down on the straw side, inside, pushing the liquid down the straw, and you've got the same air pushing down outside the straw. And so if you're going to have any sort of balance, of course, those two levels are going to have to be equal. But we don't have an open end on our straw here. We've closed our tube, which means we've got air pushing down on one side, that pool of mercury. Meanwhile, we've got that column of liquid mercury in our tube also pushing down. And so they're only going to be able to achieve balance when both weights are the same. So effectively, what we see here is we've got a column of mercury, about 76 centimeters of it, which has a certain weight being pressed down. It turns out that's going to be matched by the weight of air pressing down on the pool of mercury as well. But air is much, 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 much less dense than mercury. And so you've got to imagine the amount of air required to push down, to push or maintain 76 centimeters worth of mercury weight in a tube has to be pretty significant. And it is. On the Earth, our atmosphere is about 110 to 120 kilometers thick. You have 120 kilometers of air pressing down on you right now. That you don't feel. Why don't you feel it? Well, we've evolutionarily kind of existed in this kind of environment for a long time. Our bodies are used to it. But every time you go up in an airplane, every time you ride up a hill or a mountain, if it's significant enough, you can feel the air pressure difference in your eardrums. As you go up, you're going to find that, yeah, your eardrums kind of pooch out, and that can sometimes hurt. You have to start chewing some gum, working your jaw, do whatever it is, because your body actually has a mechanism. It has a little tube connecting the inside of your ear to effectively the outside, so you can try and balance things out. That's no different than that straw open on both sides. You're going to see the level of liquid, in this case it would be air pressure, is the same on both sides. So effectively, we're measuring the weight the pressure of the air with a corresponding weight or pressure of liquid mercury in our barometer. That's what we're doing. Now again, most barometers use mercury as the liquid. That's because mercury is one of our metals that is liquid. There aren't too many metals that are liquid. Mercury is one. Gallium is usually a solid at room temperature, but it will melt in your hand. So effectively, it turns out mercury is quite dense, and that's a good reason to use it. We can use mercury, it's quite dense, and that 110 to 120 kilometers of air pressing down on our barometer will be able to push that mercury up 760 millimeters up that tube. In other words, we have a liquid pressure measure of the gas pressure. If I can push up 760 millimeters of mercury up a tube, as the air pressing down on the other side, then that is a unit of pressure. 760 millimeters of mercury is a way to measure that gas pressure. Another unit that is pretty much equivalent to a millimeter of mercury, it's not exactly equivalent, is that 1 millimeter of mercury is often referred to as 1 torr. Torr is named after the Italian scientist Torricelli. So again, no capitalization on the T, but oftentimes you might see a capitalization if you're treating it as a unit. The reason these two units are technically not exactly the same is, of course, a millimeter of mercury is not always a millimeter of mercury. If I change the temperature, I'm changing the density of mercury, which means 1 millimeter of mercury may not weigh as much as it did at a slightly colder temperature. So the millimeter of mercury is a temperature-dependent unit. It's going to change a little bit on you, whereas the torr is temperature-independent. But they've essentially been set pretty much equal to each other in how we've defined things, and so we're going to use them pretty much interchangeably under the assumption that the difference is not really noticeable. Usually the difference is in about the 4th decimal place. That's perfectly fine. So, to give you a sense of how important using mercury had to be, just because it's so dense, look, the atmosphere pushes mercury 3/4 of a meter up a tube, 76 centimeters. That's over 3/4 of a meter. If we wanted to use water as the liquid to measure our pressure of our atmospheric gas, we're going to need a lot bigger tube. That's because mercury is over 11 times more dense than water is, which means the column of water would have to be 11 times bigger than the column of mercury to give us the same weight pressing down to balance the weight of the air. That means that if I used water in a tube, that water would have to effectively be over 10 meters up the tube. And the picture I'm using here is an Olympic diving board, a 10-meter diving board. Here we have our little barometer from the previous slides. You can get a sense of how small that would actually be. There's our 76 centimeters or 760 millimeters, works out to about 2.5 feet of mercury. If I wanted to measure that exact same atmospheric pressure using a water-based barometer, yeah, it is going to be 34 feet, a little over 10 meters. It's going to be slightly above the top of the diving board, maybe between the feet and the knees on this diver here. Obviously, that's not going to be very conducive to making measurements, and certainly not very conducive to making very detailed measurements. And that's part of the reason why they used mercury. So we've introduced the variables used to describe a gas. We've introduced the way that we can measure a gas pressure. Of course, nowadays we tend not to use necessarily barometers. We have electronic pieces of equipment that can do this. But what we're going to find in our next lecture that I'm going to have posted tomorrow, Wednesday, March 25th, is how we then use the ideas of a barometer to actually measure a gas pressure. We will get into our simple gas laws. We will do some problem solving associated with that, and then we'll try and connect some of that to stoichiometry. So we're only going to have another 2 to maybe 3 lectures on this gas module, and then we'll start moving into our next module after that. So again, first 4 chapters of this course, very, very detailed, covering everything in the textbook in those chapters. We're picking bits and pieces because a lot of this content you're going to see again in courses like 1050 and 1051. That will finish our lecture for today. Again, I hope you are safe. I hope you are taking care of each other, that you're all doing the best you can in these circumstances. I know it can be very, very trying. But of course, the more that we work together to help solve this crisis, the quicker we're going to be at the other end of it. So I am thinking of each and every one of you. Check out today's daily assignment, get that done. Check out the announcement section so you're not missing any information related to this course. And we will see you again next time. Have a good one, everyone. See you soon.